So, that thing on the screen. I like music theory, I like it a lot. It's the thing that I like studying probably more than any other thing. And I can sum up the reason that I love music theory in one sentence, which is a weird thing to be able to do, because it's like something you love, it's supposed to be complicated, but I picked one, and it seems like it covers everything. So I love music theory because it's a discipline that's so technical and so complicated, and it's got so many formulas and like principles, but in the end, it exists to describe an art form. Like when I talk about, God, raising the 5th scale degree to make a dominant chord starting on the 3rd scale degree that'll tonicize a relative minor, I'm not talking about like an engineering problem, I'm not talking like about some algorithm to solve something or prove something, I'm talking about the things that an artist uses to like create a piece of expression. And there's not another discipline that works like that, and if there was, I would have found it. And those are qualities that turn some people off, because like, you know, it's too technical for the arty types, you gotta be drawing charts all day and stuff, and then it's not, you know, technical enough for the sciencey types, because you draw charts all day and you don't even get to be objectively right about something at the end of the day. But for me, it's just right, in a Goldilocks kind of way. And so I want to try to just explain to you why that is, and prepare you to listen to the results of my own engagement with music theory. All right, slide 2. See, the goal of music theory is to describe the way that people interact with music, and both as listeners and as composers. And that's the really important part. Music is a human phenomenon. It's not just something that exists that we can study from the outside. So however much it seems like we're talking about the ways notes work, we're really talking about people and the things that they choose to do and react to. And so right away you can ask a pointed question that really deflates the argument a lot, which is which people? Because it's an art form, every listener's reaction is unique and unpredictable, and every composer's methods are their own. So like, if we were claiming this was a scientific, empirical discipline, yeah, that would be it. You win. I wouldn't have anything to say. And that's the depth to which it's not. It's not an empirical discipline by the basics of its definition, by like the thing that makes it what it is. It's not a science. And it'd be like trying to think of like color theory in visual art, or like narrative guidelines in like fiction writing as a science. You have some principles, but in the end, they're just going to draw or write what they think is good, and you just get to say whether you like it or not. So, let's see. But there's no other means of analyzing art that gets as elaborate and as science-like as music theory does. And now you see, when people say that they've studied music theory, they're usually talking about the theory of the Western classical canon. And that's a very broad label. It covers just about everything that you would think of if you hear classical music, and then probably a lot of other things that you probably wouldn't think of. And it's theory like, it's achieved that kind of ubiquity through some cultural imperialism, we should acknowledge, but also because it's kind of the only place where music theory has become a discipline, become something that people study in the way they study a technical field. It's so quantitative, it's got rules and formulas, and like it has something to say about like almost anything you can do with notes. And it's also like very widely applicable. Like you can use it to talk about so many different kinds of music from different places in the world, from different cultures, and you'll see that music following the rules that you learned about, even if the people writing the music don't exactly know that they are. Like minor and major keys and like harmonizing and cadences are all Western classical canon musical concepts. And so when you get a theory that's this concrete and this like wide-ranging, you get people that start to think that they're gonna like figure it all out. And like they're gonna find the principles that lead them to just the best way to do music. And like sometimes they're appealing to science, you know, trying to like appeal to the qualities of acoustics to like develop the ultimate sound, or like sometimes they're appealing to religion, saying that musical structure is something divinely created by, you know, the same thing that created ears and sounds to hear them with, or sounds and ears to hear them with. You know. Yes. God, my notes are out of order. I'm sorry, everybody. Yes, okay, sorry. But we've been over this. It's an art, you don't get to solve it. And that's an important principle that is going to come back. If there's a correct, a perfect way to do it, there's no room for creativity. It's like a math problem. Art needs freedom. A complete explanation of the function of music is not a goal, not just because it's something we can't do, but if we could, music would no longer function as an art form. So we're looking for something less than that. We can't prove things, but we can recognize patterns in the way people tend to write music and in the way people react to it. Not universal patterns, but they're there. And so we use theory to describe the shape of these patterns and talk about them. And then we can turn it around, and where we looked at music to develop theory, we can use theory to create music. We can expand and we can tweak and augment those patterns and create new and exciting ones that are just bigger and more complicated, but they're still based on the shapes that we identified that people reacted to. And the only way to do that is to set some rules. Patterns only exist if you repeat something and if there's a way that things are done. And so we don't set rules because we think we have it right. We do it because we need to. We have to pick one path, even if it's a little bit to the exclusion of other ways of looking at music. And music should just be an exploration of those possibilities. I've done my own thing, I've followed my own path, but it's not because I think other ways aren't valid. The only approaches that I call illegitimate are the ones that call other approaches illegitimate. When somebody looks at their study as like a search for truth, that's just treating music as something solvable again. So I'm going to tell you about my particular path. It's not the right one, it's just mine. And I think I put enough effort into exploring it that it'll be worth your time to hear about. So, first of all, my approach uses 12 equally spaced tones, like piano keys. Many different kinds of music use these 12. Their scales will be based in some of the 12, if not all of them. And I like it because it's just very intuitively organized in a way that a lot of people find meaningful. And, I think that's it, yeah. It's just intuitively organized in a way that a lot of people find meaningful, and you can use it to talk about so many different kinds of music because so many different kinds use scales that are based in those 12 notes. So, I'm going to start from the bottom because in a way I've started from below the bottom with the philosophy and all that. And so now we're at the bottom and we can actually get into the thing. So the idea is music is sound. Sound, you can see, is vibrations that travel through a medium. And if that vibration is happening at a consistent rate, it has a frequency. It's literally just the frequency with which the wave goes up and down. And to a listener, frequency creates the sensation of pitch. And greater frequency, you can see greater frequency, smaller wave, higher pitch, lower frequency, bigger wave, lower pitch. And the thing about pitch is that it pretty much goes up and down forever. There's not really a beginning and an end of it. It goes out of the range of human hearing, but things can still vibrate at those frequencies. And so we don't have discrete units of movement. It's a continuous line. It slides rather than steps. And so how do we organize that? It had a beginning and an end. It was a whole, like circles. It divided up into parts, into quarters and thirds. But we don't have that. There's no milestones. There's no foothold on an infinite line that doesn't have any beginning or ending or stops along the way. And so in this situation, we have to measure it relatively against itself, or rather organize it relatively against itself. See, if you have two sound waves, there's a ratio between the frequencies. And that's how we organize pitches relative to each other. And if we're looking to create an intuitive system, we need to start with the simplest ratio that those two frequencies can have, which would technically be 1-to-1. They're the same, but we're trying to describe different pitches here. So we go to the next simplest, which is 1-to-2, and that's where we get somewhere. I've drawn a 1-to-2 wave right here. You can see the in the same amount of space, that one waves twice, that one waves once. And when the frequency of this waves has this ratio, frequency of two waves has this ratio, one is twice as large as the other, the notes that are produced will be an octave apart. And an octave is like the fundamental organizational unit of so many different kinds of music. Almost all schools of music theory, I'm not sure there exists one that doesn't acknowledge the octave. If it does, it's very obscure. Because like 1-to-2 have to hold, that's like the simplest relationship that two quantities can have without being the same as each other. And so what an octave does is you get the concept of pitch class. See, the idea is two notes that are one octave or multiple octaves apart will have the same letter name if we're using letter names. Like it's an E, this is an E, E. And you can hear that like, while they're different notes, they're clearly related to each other in a way like this note isn't. See, and so we get a system that repeats itself every octave. So like all the letter names start over, and you're going to see later lots of other things start over. We have the octave is like the fundamental unit. We've created a discrete unit out of the doubling point of a frequency because it doesn't have discrete steps just inherent to it. Okay, so good results with one small interval. So we keep going. The next simplest ratio is going to be 2-to-3. And this ratio creates the perfect fifth, and that's what I get the rest of the 12 chromatic tones from. You see, okay, the way you do that is through stacking fifths, which is just like you take a note and then you go up a fifth, and then you go up a fifth from that one, and you keep going. And the thing that happens with fifths, with this particular ratio, is you stack, and every time the fifth hits a different spot, or well, the note hits a different spot in between the two octaves, or two ends of the octave. And so, like, and then after 12 of them, it lines up again where it started here. So you can see this distance between two dots is an octave. This is a fifth. You can see they line up over here, and every time what's down here is, you can see like the yellow one falls in the middle of these two dots, middle-ish towards the bottom, so it's here. And then the blue one over there falls right next to it, its position roughly, so it's next to it. And then like the sort of dirty yellow one is right next to the octave, and so it's right next to it. So you get this system that outlines 12 different points on the octave just from this one ratio, from stacking it against the simplest ratio. And all of the intervals that you can create between those 12 points on the octave, you can see there's a table up there. They have their own nice compact frequency ratios. You're not going to have to memorize them all. And so that's the system from which we get the half step, just the smallest unit of measurement in a 12-tone system. It's the distance between two piano keys that are next to each other. And it's based, it just comes out of the relationship between just two frequency ratios. So let's see. The problem is, though, that none of that actually quite happens because the math doesn't really work out. It's annoying. The math doesn't work out, and 12 fifths ends up just a little bigger than 7 octaves. You can see it, like, it's a little off there. And so this has been a historical problem. There's come up with a lot of ways to deal with it, and they will argue about them at length, but there's one that I and most of the music that you've probably ever listened to, most, not all, gravitates towards. In equal temperament, you just kind of make every fifth a little bit shorter, so they fit. And the thing about doing that is that the ratio between the two notes of a fifth are no longer exactly 2/3, and none of the other intervals have their nice, even frequency ratios anymore, but they're close. And so, yeah, obviously that solution, it feels a little crude. It's just saying like, oh, well, I mean, it's close, we just changed them a little, it's no big deal. But I think it's the one that's true to human intuition, and that's what we're trying to do here. We're just trying to describe the way people look at the system. So like, we instinctively round ratios. We don't think of like 21/30ths. We, think about basically 2/3. An untrained ear probably isn't going to notice a change in pitch that small. And if it is, it's going to be because you put the two right next to each other and said, hey, listen for this. And what we get for that compromise is we get 12 pitches that are perfectly equally spaced. So each half step is the same as every other half step, and then each interval that you create out of combining half steps is exactly the same as any other interval, no matter where it is. And if you like try to preserve the nice frequency ratios, then you get half steps that are different sizes and intervals that are different sizes depending on where they are, and then you lose some things like all of the really great organizational properties of the number 12. Hey Mom, I'm going to just validate the crap out of your favorite number. So when you have 12 equal steps, you can really treat it just like the number 12. All the divisibility of 12 applies. And you see, the thing about it is that it's divisible by every number under 6 except for 5. It can't be divisible by anything over 6 because that's more than half. But we're talking about intervals, so we have another factor here. You see, for any interval over the divisions, it's based on, the gray notes, gray dots represent half steps, and then you can see there's intervals that jump in groups of 2, 3, 4, and you can see the way that they line up with the octave. They divide it evenly, and then the one that's 5, I have another pink dot up above to signal that it just keeps going, again, around that whole system. So what gives us the second half of the chart is the fact that every interval greater than 6 can be inverted into a smaller interval because of the nature of pitch class. You see, let's see, if you have to go more than 6 steps to reach another note, you can get there in fewer by going the other way, like this. I've drawn out on a piano keyboard. Going from here to here, it takes 8 steps going this way, but you can get to a different note, but the same pitch class. It's an octave away by going a smaller distance. So we can basically just group anything over 6 into the same category as the other 6, which gives us, 6 categories that any relationship between any 2 notes in this 12-note system can be put into. And then 5 of those split the octave into equal parts, and then the one remaining one just stacks until it's hit every pitch in the system before it's returning to where it started. And you can see the second half of that graph is 7 inverts to 5, 8 to 4, 9 to 3, 10 to 2, 11, back to 1. And so it just goes back the way that it started. And then 7 half steps is actually the 5th, the original interval that built all these steps. And so that inverts to 5 half steps, which is a fourth. A fourth has 5 half steps in it. It's the worst thing in the world. But it has the same qualities as the 5th. It stacks in the same way. You go through the same set of notes, but backwards, because it's backwards or upside down or inside out. It's words. You can describe it if you want to. Anyway, so I hope you can see, just the way everything lines up here and how nice and organized it is. And I hope that it's just clear to you, because that's all I can do. Because all this categorizing of ratios and divisions isn't going to let me prove something to you. like, I just have to show it to you and hope that you see it too, because this is all about an art form. You remember? God, so like, and that is a wall that you sort of run into when you're studying music and studying theory in the way that I have. Like, I spent a long time drawing little charts with dots, like those ones that you've seen in a little graphing paper notebook that I sadly lost just a few days before this presentation, or I would show you. It'd be very nice. And see, when you're arranging and rearranging notes like that, and looking at the patterns and looking at the ways that they line up with each other, you start to feel like you're getting somewhere and like you're going to break through to a central truth that's going to make it all make sense. But you won't. It's a whole thing. It's essential to the nature of art that you won't. And so you start to wonder like what your goal is in approaching the phenomena of music this way. And I think the answer, or something like it, lies in an important unsolved problem in math. Let's see. So the question comes from computer science. It concerns problem solving. It's whether the class of problems P equals the class of problems NP. You win $1 million if you figure that out. It's a big deal. Now with a lot of simplification, because unsolved math and all, P stands for problems that can be solved quickly, and NP stands for problems where a given possible solution can be checked quickly. In this case, quickly just kind of means in the same time frame. That's the sort of weird ambiguous word you have to use to phrase the rest of the problem in a way that makes intuitive sense. And so if they're equal, if these two classes are equal, then being able to check and answer quickly means that there exists some way to solve that problem in the same time frame. And so the classic example is Sudoku, because it's a very good example. See, when presented with like a filled out Sudoku grid, you can check pretty quickly to see if it's been done correctly. The process of scanning every line in square is like, it's a little tedious, but like it's much faster than trying to solve it from the beginning. And it certainly doesn't involve any like difficult calculations or decisions. I think I went a slide ahead. Yes, I did. Okay. Excuse me. Yeah, and so that's the essence of being an NP problem. You see, computers, they can check a Sudoku grid like almost immediately, and they can still solve it faster than humans because they're made for solving problems as fast as possible. But the thing is, as you make the grid bigger, as you increase the complexity of the problem, a computer can still check it very fast because it can just run down those lines as quick as it wants, but the problem, solving it from the beginning, gets much, much harder at an exponentially faster rate. And see, the general consensus is that P does not equal NP. That, like, there are questions for which finding the answer is just much more hard, exponentially more hard than checking a given answer to see if it's right. And you see, if it did, then if P did equal NP, then there would be a way to solve a Sudoku puzzle that's as fast as checking it. And you know, maybe there is, and we just have to get really good at Sudoku to find it. But we've been doing Sudoku for a while and we haven't, so it kind of suggests that there's probably not. And then, if there was that kind of ultimate solution, it would sort of ruin Sudoku as a puzzle. And does that sound familiar? Because it's a thing. See, oh my god, sorry, these are out of order again. Puzzles. Puzzles are made to be enjoyable by people, and so is music. And you see, the things that make Sudoku an NP problem make it a good puzzle. The process is difficult, takes like thought and calculation, but when you get the right answer, there's an aha moment. It just all makes sense, it hits you, and you suddenly understand exactly what you need to do. And most good puzzles are based on NP problems. Like, the solution is gratifying because you can instantly see that it's correct, but also because you can't develop some easy formula to find it. Now, there is an important difference here. Puzzles are solvable, and I made a whole big thing about how music is not. So, like, if someone asks you if composing music is an NP problem, you should say no. Tell them it's because it's not a decision problem. You don't have to know what that means. You'll sound smart. It's whatever. See, what I think is relevant about this concept is just what it says about the way people process information and then the way that information exists. These are computer science theories because, like, we came across them through computers, but they're really just deeper questions about things that we can and cannot know and cannot do. And so I see these theories of complexity as like kind of the link between the concrete and abstract, and the thing that makes art and intuition meaningful in like a mechanical universe. So back to these 12 tones and all the charts. They're organized, isn't it? Things, they line up. And that's sort of what we recognize in music in the place of solutions. That like aha moment of figuring out a puzzle is similar to the satisfaction of hearing an organized musical structure happen. The thing is that in like actual music, you know, the notes aren't lined up neatly in rows and, you know, stacked in, you know, consistent sizes. They're just layered in intervals. Intervals with different qualities are layered over each other to create chords. Chords are put one after another to make progressions, and the complexity just explodes. And from both ends, like from listener and creator, listener and composer, like music is the process of working with structures that are too big and complicated to comprehend all of the way. But we can still see the organization in them without being able to like articulate all the factors that create it. We can sort of identify the solution of that order without being able to solve it as a problem. And so learning theory it's the process of being able to see the order in more complex structures and follow that increasing complexity just a little farther before it goes off into the unknown and the unknowable, and we can only understand it intuitively. So just studying, charting out shapes, and getting like familiar with the system is going to get tiring after a time. It has. Music theory is for composing, and it's for exploration. It's for creating structures that work in new ways and seeing what kind of order and organization you get out of them. And as you know, I did that. So now I want to get to just telling you about the shapes and the synchronicities that I find in the 12-tone system, with a focus on the ones that I thought about while writing this piece that you'll shortly hear. And that's all I can do, is just kind of tell you about my process and hope you see the things I did, that you'll look at this big, unknowable structure in a way that is similar to mine. So let's see. So the fifths and fourths, those are those foundational intervals that line up to make all of the other 12 points in the octave. And they're 5 and 7 half steps long. And so you can order pitches by fifths in the, just a minute, this order, this one, down here, in the order that they occur, or no, I'm sorry, in the rainbow order, not this. This is how they're ordered just next to each other in the octave. But if you order them in the rainbow order, in the order that they occur in the big stack of fifths, then you start to get a lot of important musical constructs. And then when you go 5 or 7 steps around that cycle, just through that, you know, well, the circle of fifths, you get 2 important harmonic constructs. When you go, again, 5 or 7 steps, specifically, you get pentatonics in the natural modes. 5 fifths stacked, then put into 1 octave is going to make a pentatonic. 7 stacked, 1 octave is going to make one of the natural modes. And so what these are actually, pentatonic scales are like the basis of just endless like folk and popular music. We go like this. Like they're simple and they're just extremely melodic. They're maybe the easiest way to arrange notes in a way that sounds like music. And like when a popular singer like noodles, like Mariah Carey at the beginning of All I Want for Christmas, like all I want for Christmas, you know, that she's moving along pentatonic lines. And so like when I want to include a pattern in the piece that sounds sort of conventionally melodic, you can hear pentatonic shapes start to happen. Oh, and that the piano is at the bottom there. Actually, I made the chart like this because this structure, the 5 making a pentatonic and the 7 making a natural mode, is how a piano is set up. The white keys form a natural mode. Black keys form a pentatonic. And because like the people that make keyboards know that that's a way to intuitively set up so that when you're working within musical systems, like, things make sense and you can see the order of the things that are happening. So natural modes are more complicated because they have more notes in them. That's how it works. So the thing is, there's 7 of them, one for each sort of white key in the octave. And 2 of these modes, Ionian and Aeolian, are better known as like the major and minor scales, which obviously show up in the music of numerous cultures. They're like one of the few music theory terms that non-music theory people like know and can recognize. And now you don't have to just play them on the white keys. Obviously, like, everything's relative, remember. So all that matters is that that pattern is the same, and I feel like visualizing them, you know, like a piano keyboard relative to each other isn't the most helpful way to think about them. It's kind of more the fastest way to get your student to play a Dorian scale so they'll leave your office. So I prefer to think of them starting all on the same note, like that chart, and laying on top of one another. And so when you do this, it's easy to put them in an order where you change one note at a time to get the next one. And this note changes. This one, I don't think I went in order, I'm sorry. Here, 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 here. And the thing is, the note that you change is always going to move by a fifth. These things are going to keep showing up like there's just synchronicities that you can make sense of. And it's also kind of the thing that leads you to want to believe you're going to find some ultimate solution. Is like, oh man, I'm seeing it. I'm seeing the code and seeing it in the matrix or whatever. But let's see. So this order, this one in the chart, is important to my piece, particularly like the second and the third movements. Much of the second is focused on the relationship between the Lydian and Dorian modes, which are this one and this one. You can see that they're the same number of steps apart on this system as the Ionian and Aeolian modes, 1, 2, 3, 1, 2, 3. And Ionian and Aeolian are major and minor. They obviously have an important relationship that a lot of music has explored, and so I wanted to explore that same relationship between 2 different constructs. And I think I actually figured out just earlier today that maybe some reason why jumping 3 modes works so intuitively is because 3 kind of has the same relationship to 7 as 5 and 7 have to 12, where if you keep stacking 3s, you'll hit every point of the 7 and then come back to where you started. With the Lydian and Dorian modes, in the second movement, I would usually lay them over each other. So using notes from both to create like new shapes, kind of a new combined harmonic space. So let's talk about for a minute, or actually, the third movement. In the third movement, I spend a lot of times actually like decidedly in one natural mode or another, where in the other 2, it's not usually going to be that straightforward. It's more complicated, there's just more things going on. But the thing is, the modes shift constantly, and they're usually either to the next one along that cycle, or by that same 3-mode jump between Ionian and Aeolian, or Lydian and Dorian. You gotta memorize the 7 names by next week, by the way. On my desk. Anyway, so now let's talk about what happens when you don't follow the fifths for a little, because we've been doing that because it's very fun, but there's other intervals. Sorry. So those intervals, for one thing, actually the half step itself is basically 1, and so 12 is divisible by 1 in the way every whole number is. And then you have 2, 3, and 4, which create like these stacks that divide the octave evenly. And the thing about the way they sound is it's interesting. You'd think that something that splits the octave evenly would sound like nice and organized and at rest, but they all make really tense and dissonant patterns. That's stacks of 2, stacks of 3, stacks of 4. And so in the first movement, I use these a lot, pretty extensively. but the way I approach it is I break them sometimes. Like, as in, I add one note that doesn't line up with it perfectly, so that usually that will like create a fifth structure between that note and one of the other notes in a system, and it's just sort of like a little glimmer of nice consonant sort of sound through like all of the dissonance and kind of chaos. So let's see. So the second movement. Overall, it's kind of a progression from like harsh, disorienting harmony to more gentle stuff. The idea is I felt like a lot of the music I was writing, I was just falling into conventional patterns and just things that I'd been taught prescriptively and I knew worked, rather than really creatively going out there and creating new things. So the first movement, is kind of to really aggressively break me out of the conventional habits. It's totally atonal, and rhythmically it has an approach. It's called additive rhythm. The idea is there's not a consistent time signature. Phrase lengths are constantly changing, and the music is basically moving in just little chunks of like 3, 2, and 4 that just alternate. They don't go in a consistent pattern. And so basically it's unpredictable and you can't tap your foot to it at all. So the second movement is a slow movement. Contrast the other two. It's sort of intended like to get a little bit more conventional and nice sounding as a harmony. And I wrote a theme for it, like a 8-bar theme that it returns to periodically, once just as an identical repeat, then again as just a big expanded distortion, and then a third time as a variation but a less out there one. Because like repeating something is the simplest way to create a pattern, and repeating with variation is the simplest way to create something new that you can still perceive as related to what happened before. And that theme is actually, it's just 8 measures of 4/4, which is going to be like the one instance of a normal time signature in the whole thing. And this is the one where I mentioned I explored that Lydian-Dorian relationship. And because I was working with natural modes and working with structures based on fifths, it allowed me to come a little closer to conventional harmony. But only a little, because I put them over each other and looked specifically for the ways that they conflicted and played them against each other. And so the third movement is brief, much more so than the other two, and it's intended to sort of be a return to as close as I at least care to get to conventional normal sounding harmony. And like having it be informed by all the exploration that I did for the last 2 movements. The hope was that, I could write something that like sounded a little, more conventionally nice and not harsh. Well, not just like, falling into habits, going through the motions of patterns that I know worked. And that was kind of just what I'd hoped writing this whole piece could do for me, and the place that I hope to arrive at the end of it. And it's sort of a microcosm of that whole compositional philosophy, the desire to write things that use your knowledge of theoretical rules and are organized according to them, but are still like free and creative and they're impossible to pin down. And so it's the piece is kind of just a personal expression of where I'm at, coming to understand this system. It's not the grand statement that epitomizes all the things that I've told you here, because that's not a thing you can do, and the whole point is that's not a thing you can do. And it's kind of also my first attempt at like writing something really long form that really demonstrates all this knowledge I have and really is like a full use of what I feel like my abilities are. And that's sort of where its name comes from. It's titled the Bildungsroman Sonata, which is the German word for the coming-of-age novel genre. And for one thing, that's a fun German word that nobody appears to have used as a sonata title before. But also, like, it reflects, for one thing, it's just topical, I guess I am, and such. But also, like, there's more subtleties to that genre and how it's about, like, the entry into adult life as being a real and full person, and like addressing the complexities of the world in a full and meaningful way, and that's sort of what I feel like the process of really using all the theory knowledge I have and applying it to something is. And so that is everything I have written down, and you can hear it now. Let's see. I'm going to, I should have had something, I have something to put on the screen while I was playing. So I'll just turn the display off.
So this is Carol Erfourth.
Yep. Actually, sorry.
I have to say, it's interesting to play a premiere of a piece, because I can honestly say that there's nobody in the world right now that could sit down and play this, except me.
Yes. Can I ask you before we start to say the title again?
Bildungsroman.
Bildungsroman.
Bildungsroman.